Okay, let me show you how we're going to turn what we're doing into a proof. You'll probably want to kind of shift to notes. We're going to call this topic 4.3b, which is still verifying but we're going to be verifying algebraically, which again, most kids remember as a proof. Okay, now if you're already like wondering, well, is this like a geometry proof? Well, I guess it depends on what you mean by that. You're going to, yes, have two columns, and in one column will show the work, and the other column will give a reason. But give this a chance because, well, these are trig identities. So, you know, in that way, they probably aren't like our geometry. But let's see. What I've done is actually created, what are we going to do? I think we're going to go through we're going to go through 4 problems, hopefully, that each kind of have a category to kind of help you guys get a feel for how you can start to turn these problems into proofs. The first category here, I'm just kind of coining using basic identities. Using basic identities, maybe a little bit like the first problem on your mini check. Now, as you'll see here, since it's a proof, I'm going to tell you that cosecant squared over cotangent is equal to cosecant x secant x. So we're telling you that it's equal because now the objective has changed slightly. What we want to do is we want to prove, we want to show why that's true. We will use this kind of this 2-column method. You can prep for that if you want. Now, there is one thing here that we kind of have to be careful about, and that is this equal sign. We're so used to throwing it around. It's used a lot in math. But you got to understand that what we're actually trying to show is that the left side equals the right side. What that means is that we can't say that it's equal, meaning we can't do something across the equal sign. Maybe the most common mistake is when kids will accidentally do something to both sides, you know, like multiply by the denominator. I just want to show that right now that you can never do that. You can never move things side to side because you don't know that it's equal. Instead, you're trying to show that it's equal. So what that really means is you just pick one side and you try to make it look like the other side. What side do we pick? It depends. A lot of times you pick the side that's more complicated. That also depends on what you think is more complicated. But I'm going to pick the left side. There's some things that I can start to do. That is, in this case, I can start to interpret the numerator. Now you'll notice that I'm interpreting the numerator as a cosine times cosine. And that allows us to get started right away with, okay, what was kind of the reason for that? What would I write on this side? And sometimes the reason is just going to be algebra. Now, try to be specific with your algebra. In this case, we basically interpreted the exponent. I'm just going to kind of loosely write the word exponents. Okay, that's not a theorem. That's not a property. It's just more algebra. But we basically interpreted the exponent. So that's good stuff. Now, look what happened. Okay, don't feel like you have to know the final answer. But look where we are right now. I have half of my proof accomplished. You know, I have a cosine over here. I'm supposed to get a cosine over here. So that's good. And that also means that I'm going to let that alone. Instead, I'm going to, or for the sort of the remainder of the problem, I'm going to mess around with the cosecant and cotangent. Now, to mess around with the cosecant and cotangent, there might be a variety of things. Maybe I don't want to have a denominator. Okay, well, I don't want to have a denominator because I don't see a denominator over here. So I'm going to now choose to change the cotangent to be a tangent. Now be careful, when I say change it, what I'm actually doing is applying an identity. Now, if you use an identity, you have to be specific. In this case, I used a reciprocal identity. So again, I can't just say identity, but I have to be specific. Now, It's all right if you just write reciprocal. You don't have to write the word identity after it, but I assume that you realize that's what that means. I would say that it's a little bit too much abracadabra if you go like this and say, oh, that equals secant. Now it does, but it's a little too abracadabra to take this and just say that. I think we need one more step in here. We need to somehow show how, because that's not a straight up identity. So let's do a little how. Let's do a little how to. And I hope that as you look at this, you start to realize that each one of these has sines and cosines. You know, in essence, cosecant is 1 over sine. And in essence, tangent is sine over cosine. So we're going back to that most fundamental strategy where we change everything to sines and cosines. But you got to give a little reason. And I actually did 2 things here, which is fine. I'm showing you guys what you're going to be allowed to do. So one of those was a reciprocal identity, and one of them was a quotient identity. So again, I'm being specific. The reciprocal identity was the 1 over sine. The quotient identity was sine over cosine. Okay, you see where this is headed? We're going to be able to cancel the sines. We're going to get 1 over cosine, and sometimes we get a little excited and kind of finish the problem because 1 over cosine is secant, and that's exactly where we were trying to go. I did do 2 things though, so I should mention them. One of the things I did was cancel the signs. You can just write the word cancel. Some people would have said they divided. That's fine, you divided. And then I did come up with that final answer using a reciprocal one more time. Reciprocal identity gets the cake for this one. Basic identities, not implying that it's easy, but basic meaning I really just could take what I had, I could keep changing it, and eventually things canceled. Voila, we get cosecant secant. Okay, but you could say we proved it. Okay, I'm going to kind of keep going. Today's lesson is designed carefully that I have 4 proofs. Hopefully we can do all 4. We might have to skip some steps in one of them, but let's talk about common denominators. Obviously getting a little bit more specific, a little bit more technical. Tangent plus cosine over 1 plus sine equals secant. Again, realize what's happening here. It's like I'm giving you the answer, which does make this process a little easier. Okay, now we've learned or we've seen a number of problems where we've used common denominators. This is a good example of it because basically, as you stare at this, I want you to realize that what you have are 2 fractions that are being added together. When you have 2 fractions that are being added together, well, that's really the only thing you can do, which is to use a common denominator. Do you see the 2 fractions? One of them is this sine over cosine. So of course we have to change it. Quotient identity. Be specific. Now, I know I'm moving along a little bit quickly here just for time's sake, but you can still look in your little book. I do kind of wonder though, are you starting to say, okay, yeah, tangent is sine over cosine, something that you're getting to know. Eventually that's something that you want to know from memory. Okay, but you can keep looking in your book for now. All right. Okay, there's no sort of other option here except to try to add these fractions, and as we've said, using common denominators. Okay, now this is an example of a problem where whatever is not in the denominator is what I need to put there. So this cosine does not have 1 plus sine. I need to put it there. Now that means I also need to put it up here, because you always do the same thing to the numerator and denominator. This denominator is missing a cosine, so I have to put it there. Now, you guys should feel like that you've seen a problem like this. I don't know if it's the exact same problem, but I know that either in an example or in a homework problem that this type of behavior was happening. So, I've carefully shown you guys problems to get you ready for this point. And this point is that you say, okay, that's what I want. I want to get a sine squared. Okay, I want to get a cosine squared. Okay, this is good stuff. This is the way this is supposed to be working. The other thing here is you don't need to have two fractions anymore. Like, you can add the numerators and sort of just group this together as one fraction. That's what you're trying to do anyway. Okay, so I'm going to kind of move to that version. I'm going to move to the version where there's one fraction. So we have sine plus sine squared plus cosine squared, all in the numerator, and then we have our common denominator. What reason would you give? Kind of what would you write on this side? This is pure algebra, okay? But I want you to be specific. Don't just say simplify. So I think that it would be wise to say common denominator. That means that you made a common denominator, and I'll give you credit for that. You also technically added the numerators. You technically did addition. So we could say common denominator / addition. All right, so kind of keep track of what's happening. Be able to prove by writing down what happened that you understand. How you guys feeling here? You feel like you're able to finish this problem? Sine squared plus cosine squared equals 1. I thought there'd be a little more excitement about that, but sine squared plus cosine squared equals 1. Now, I do want to pause at that because, boy, if you're going to use a Pythagorean identity, say so, okay? Make sure you say Pythagorean identity, or Pythagorean is fine, but you have to be specific. Now, I know fractions still make us shudder a little bit, like maybe you're not sure, am I allowed? Okay, what I mean, am I allowed to cancel? Well, yes, you are, because this is a pure multiplication problem. And as long as I have multiplication, I don't have to worry about a heart method or something like that. I can just cancel factors. So yes, these cancel. Now you're still left with cosine, but maybe more specifically 1 over cosine. Be careful about that. Notice cosine's in the denominator. And then that's going to equal secant. We did kind of do 2 steps. I sort of just blended it because of the space I have here, but we either canceled or divide. I'm going to use the word divide this time. And then there was a reciprocal to finish this out. Are we having fun yet? Usually it is. I don't know what it is. Maybe it's that 5-letter word, proof. I mean, we try to put a smiley face on it. Come on, we're turning into a party. It'll be something memorable. This is one of the things this year that it's challenging, but in a good way. And you're going to get these right. if you work on them, you'll get them right. There'll be some in the proof party. It's a 2-day party. There'll be some in the party that stump you and you come back to it. You have to be okay with that. Yes, you'll have the weekend. Some of you will work on it over the weekend. Fine. But be okay if there's some unfinished work, because you're going to come back Monday. You're going to be able to keep working on it. Whoops. I'm getting excited about the problem. Let's put down the method to keep with that. Polynomials. Polynomials. Okay, now, polynomial techniques kind of should conjure up a certain algebra type thinking, okay? When we see things that look like polynomials, exponents, plus and minus signs. Look at the other side of this. Again, it should speak to you and say polynomials. All right, so I have sine to the fourth plus cosine to the fourth equal 1 minus 2 cosine squared plus 2 cosine to the fourth. This is a good example of a problem that you really could work from either side. I mean, I'm going to choose to work on the left side, and since I'm kind of guiding the conversation, I'm sort of guiding your thinking, but some students would be successful by feeling like they could do something over here. I don't know if we're going to do it both ways just because of time, but yes, some problems could be done on either side. Okay, it's not just getting lucky. It's not like, oh, good, I got lucky, it worked. It's starting to use some critical thinking. And honestly, some critical thinking on this problem would be to observe that this side is all cosines. Yes, there's a 1, but it's all cosine functions. This side is sines and cosines. So guess what? Guess what? You want to change the sign. Okay, you want to do something that's smart, that gets us to all cosines. Okay, so how would we change the sign? Okay, well, this is a little bit of polynomial thinking, actually not too advanced, but you could change the sign to be sine squared, sine squared. Now, why would I change it to sine squared, sine squared? Go ahead, Brendan. Good. It's a cosine squared. These are equal to cosine squareds. Like Brendan said, 1 minus cosine squareds. Okay, so actually, you're going to find out that we're almost done, but it's all about being smart from the beginning. Okay, so each of these sine squareds is a 1 minus cosine squared. And just like that, everything's cosines. Everything's cosines. Just by the way, there will be some proofs that you'll do and you'll skip a step, and I'll say that's fine, but we want to be careful about what we're skipping. This would be skippable. If you said, do I have to write sine squared, sine squared? Okay, I'm not going to make a big deal out of it. If you're like, yeah, I know that that's going to become this, you could do that. But like I said over here, we want to not have too much abracadabra. You have to be showing how things can simplify if they're not an identity. Okay, so also in this one, I would expect that you're going to show some foiling. You don't have to show arrows, but you should show the result of the FOIL. Okay, like, you get a 1 and you get minus 2 cosine squareds. You can skip right to that. Now, the last part of the foiling will give you a positive cosine to the fourth. Don't lose track. We also have a cosine to the fourth as part of the original. All right, and I hope that you're feeling like that we did it. As long as you understand that that's 2 cosine to the 4th. I didn't write any reasons down. Sometimes students will do that and they'll go back and write the reasons. We could go back on this one.
So what reason would we have to go to like that last step? Would we just say simplify?
You could say simplify. If you wanted to be a little more specific, you could say add or addition. I do accept the word simplify as long as we're not using it like for every step. But you could say simplify. To kind of go back to the first step here, I would accept if you said exponents. What you really did though is you factored it. So since we're together, I want to teach you more that sine to the 4th factored into sine squared. You broke it up. But Pythagorean for sure. If you really want to know when I grade your proofs, like that's what I'm going to look for, that you said Pythagorean. Okay, because that is important. That was definitely a sine squared turning into 1 minus cosine squared. Some people would say FOIL. Some people would say multiply. Again, I'm kind of flexible. Okay, which leads us to our last one. It's kind of the big kahuna proof here. So I'm going to get rid of all this wonderful math. The category for this one, just quite frankly, is that it uses a combination of tricks. You can write that down. I'm just going to write down combination. But yeah, there's going to be some problems that you get that you also will have to do this. You have to be willing to work through some more complicated proofs. So it's going to be the sine of x equaling the sine of x over 1 minus cotangent of x minus sine times cosine all over sine minus cosine. I just want to point out here that although we're not going to use a conjugate, that don't forget about that strategy. Like I can't go over every strategy in this little lesson, but it sort of looks like maybe I could use a conjugate. And there is some truth that sometimes you don't know unless you try. Okay, I'm just guiding the conversation that it doesn't kind of help this time, but there's sometimes you don't know unless you try. So I know I don't want to sound like good luck, but I'm just being honest that sometimes you try something, it works, and sometimes it doesn't. For this problem, it's actually going to start out as kind of like a tried and true common denominator. We just have to take the plunge, as I sometimes say. You have to create that common denominator. Okay. By the way, we're going to work on the right side of the identity of the proof. Hopefully that's pretty obvious. The right side is the side that's more complicated. Now, if I'm going to make a common denominator, it's going to feel like I'm kind of recopying some stuff, but yeah, I mean that's what's needed. So I need some space already, but I'm basically going to insert what's missing from each of these denominators. And so this one's missing sine minus cosine. This one's missing 1 minus cotangent. So we kind of get those written. I would caution against trying to do too much in your head. Okay, like you want to show your work in this proof activity. Are you realizing that in many common denominator problems, and I don't want to say all of them because there's never really an always, but in many of the ones that we've done, the denominator stays factored. So kind of going with that theme, I'm going to keep the denominator in factored form right now. Okay, because maybe it's going to cancel with something in the numerator. Speaking of the numerator, we've got quite a bit that gets created here. You're going to distribute. So I'm going to distribute sine. Now I will say that, at least for starters, that seems like a good idea because you get a sine squared. It seems like when we get squares, good things happen. So we get sine squared minus cosine times sine. Careful, this is not the FOIL method. This is just sine cosine times 1 and sine cosine times cotangent. Okay, so not too many distributes, please. Not too many. Okay, so we're going to get a minus sine cosine. I would give you permission to I'll say skip, but really to understand that since cotangent is cosine over sine, I just did a quick little kind of erase there, but since it is true that cotangent is cosine over sine, and it's going to get multiplied by sine cosine, that there's some canceling that happens. So I would give you permission to kind of go right down to cosine squared. To go right down to cosine squared. Be careful, there's a minus sign there. We don't want to. And what I just said to be careful about, actually, I need to do a little better job of being careful about. Okay, I made a little mistake here. It's not bad because it's a common student mistake, and the teacher did it too. This minus sign right here, that one's pretty important. We have to understand that that minus sign is on sine cosine, and so it's really like I'm distributing a negative sine cosine. Now, I took care of it there, but it's a negative times a negative. Okay, that's pretty important. That's going to change that to a positive. All right. Kind of taking it steady as we go. By the way, I'm not going to write reasons down for this one. You would need to write reasons, but for the sake of the clock here, I'm going to just keep simplifying. But you could have written common denominator. You could have written distributive property. I hope that you're going to change sine squared plus cosine squared to be 1. So you would write Pythagorean identity. And we're also going to combine like terms to have 2 sine cosines. It's actually -2. Okay, so numerator cleaned up. It simplified down to a 1 and a -2 sine cosine. Now listen, as I look at what I have right there, and I look at my denominator, I notice that there's nothing special. Okay, in other words, the denominator isn't going to cancel with that numerator. What I'm getting at is that we are going to have to do something to this denominator. We're going to have to do something to it. The something is that we need to FOIL it, okay, because nothing's happening. We have to go that route. So we're going to do the FOIL method down here. Okay, it ends up, expanding and kind of getting all big, but I'm just foiling and getting these 4 terms. We get a sine, we get a minus cosine, another minus cosine. Okay, same kind of thing going on here. Okay, I did a little bit of kind of combining steps. When you distribute sine onto cotangent, same thing happens. It cancels just to be cosine. So that's why we get another minus cosine. Okay, and then when I do the last foil is going to be cosine onto cosine sine. That's actually going to be like a cosine squared. Being careful with negative signs, it's actually going to be a positive cosine squared. Okay, so we have sine minus cosine plus cosine squared over sine. Now listen, it's all right if you want to ask. Like if you're like, where'd you get that? I'd rather that you not just kind of smile, okay? If you really need to ask about any of these four terms, please ask. Okay, because we still got some business to do down here. The business looks like that some things can be simplified. Obviously, I'm showing you a problem that's a little harder, but I'm basically showing you that you have to be willing to keep doing, I suppose, doing things that are true. But I know you kind of get here and you're like, now what do I do? Okay, we're in some new territory. We're in kind of some new territory. But I want you to look at this and, realize that there's only one thing that we can do, and that is to continue to keep adding and subtracting. Now, it sounds simple, right? Adding and subtracting. But when I say that, I mean with a common denominator. So I haven't really seen a problem like this where we're kind of like 3. But there's no other way to do it except to put a common denominator onto these other terms. Now check this out. When I put a sine down here, I get a sine squared. That's good. Okay, getting squares. I put a sine down here, I end up putting a sine up here. We're getting pretty close to being done. If you're kind of looking at the denominator, you might notice that it's starting to look like the numerator. Okay, we have some similarities in this problem. Sine squared plus cosine squared. We were careful with the plus and minus signs, so that's good. It's sine squared plus 2 circled guys are going to equal 1. So I'm adding my numerators down here. I guess I'm actually subtracting, but it's 1 minus 2 cosine sine all over the common denominator. Yes, we have a fraction in a fraction. I know that there's a couple proofs where you guys will have to deal with a fraction in a fraction, but we're kind of getting ready to clean that up and we're almost done. See this big main fraction? It means divide. It means top divided by bottom. In algebra, there should have been a time where you said that dividing is the same as multiplying. Multiplying by the reciprocal. Now the reciprocal is just my denominator flipped over. Let me try to color code this a little bit, that you guys understand which is which. So again, I took a division problem and I ultimately changed it to multiply by the reciprocal. Take a look at the yellow boxes. They are just flipped. Which is why the 1 minus 2 sine cosine cancels. Yes, they cancel, leaving us with just sine, which is what we were hoping for. Now, I will have students say, could I just cancel it back here? I understand that's going to cancel. All right, as long as you understand that this is going to end up being sine, not 1 over sine. But that's why. That's why it ends up being sine. Not every problem is going to be like that. But as I said a few times, there will be some. Okay? And you'll work through it. At least the goal is to work through it. Before the party, there has to be sort of a pre-party. There's some homework problems. The homework helper, okay, is 3 proofs to kind of get you warmed up and get you doing some problems on your own. So start there. We need a little sunshine, so we're give you a little homework tonight. Okay, and then we'll see it tomorrow for the party. Oh, I didn't mention, well, did you read it? You can dress per party theme. Like, I'm serious about this. If you dress per party theme, bonus points can be awarded. If you're like, what are you talking about? Well, I'm not going to say, because then, there won't be any creativity. But I have had students, quote, dress per party theme. Okay?